In video 2 for chapter 8, we expanded on what we had learned about resonance, and we looked at a particular type of resonance, compounds that are aromatic. So remember, these are cyclic structures that have p orbitals on every atom of the ring. They're planar, and they have to have the correct number of pi electrons. When a molecule satisfies all those requirements, it is aromatic and it has extra resonance stabilization. So in this video, what we're going to do is we are going to start into the first of two videos that show us how resonance can affect the outcome of different reactions. All right, the first type of reaction that we're going to look at is just acid-base chemistry. So let's look at two examples. The first one we started out this chapter talking about already, so we're pretty familiar with this one, right? So in this first one, we'll just draw it out again. We know that this alcohol can dissociate to form what's called an alkoxide anion plus a proton. And if we compare that to the next one, a carboxylic acid, doing the same reaction, we find that they have a very different level of acidity. If we write out pKa values over here, we see that the pKa of an alcohol like ethanol is about 16. The pKa of a carboxylic acid like acetic acid is about 4.8. So notice that if 4.8 is 5, the alcohol is 16, that's 11 pKa units, or 11 orders of magnitude difference in the equilibrium constant. Right? We already talked about why this was. Remember that we're looking at the two conjugate bases, this one here versus this one here, and we're determining which one is more stable. Right? We said that the conjugate base of the carboxylic acid, or this carboxylate anion, is more stable because it can share these electrons using resonance, like this. Okay, so these electrons are delocalized, while the electrons up on this alkoxide anion are localized. Okay, because there's no pi bonds there. Those electrons can't be shared. They're held exclusively by the oxygen. So that makes this carboxylate anion much more stable. And we know that an acid that has a more stable conjugate base is going to be a stronger acid. All right, so let's look at these two bottom examples. So we have two types of alcohols. The top one is called phenol, so it's an alcohol on a benzene ring. And the bottom one, this is just cyclohexanol. All right, so we could use various alcohols on the bottom. I just picked cyclohexanol because it has the same six-membered ring as the benzene ring. All right, so let's predict which one of these would be more acidic, right? And the way we're going to predict it is we're going to consider the conjugate bases. Right, so let's draw out the conjugate bases. All right, I'm going to put the H plus here, so it gives off a proton. And we form a conjugate base that looks like this. Right? And for cyclohexanol, it gives off an H plus this O minus. Alright, so again, we're trying to decide here which of these two conjugate bases is more stable. Alright, so what about the electrons on this oxygen? Alright, are those going to be delocalized or localized? All right, so these electrons are localized, right? There's no pi bonds, and so there's no way for those to be shared over multiple atoms using resonance. All right, what about for this compound up here, this phenoxide anion? All right, so what we see here is this is kind of one of our generic types of resonance, right? We have an atom with a non-bonding pair of electrons next to a pi bond, right? So we can have resonance in this situation where these electrons are donated to form a pi bond. These electrons are moved over onto the oxygen. So we create a carbon-oxygen double bond like that, and the minus charge gets moved into the ring. All right, we've seen this before. We could continue to the next position. And in fact, we could continue on around the ring. All right, so right now we're here. All right, we could continue. Let's put that minus charge in there. We could continue. We could move this pair of electrons down to form a pi bond, move these electrons over here, so the minus could be here, and then it could move back onto the oxygen. All right? So, in fact, this anion is very delocalized. All right? So that's going to make that anion much more stable, and if we look at the pKa's, the pKa for phenol is about 10. The pKa of cyclohexanol is kind of like ethanol, is about 16. All right? So why is it that phenol isn't more acidic than the carboxylic acid, right? Because look at it, it has even more resonance structures than this does up here. All right? So just more isn't always the best. Okay, so what we would like to do is have more equivalent resonance structures, and if those resonance structures place the minus charge on more electronegative atoms, that's even more stable. So here we have two equal resonance forms. Both of them have the minus charge on oxygen, so that makes this anion very stable. This one has more individual resonance forms, but many of them have the minus charge on carbon, which isn't quite as stable. All right, so let's look at two more examples here. All right, so these are unusual molecules in that we wouldn't normally think of them as being acidic at all. Both, in fact, have only carbon-hydrogen bonds. So we're going to just consider this scenario. We're going to look at these hydrogens that I have drawn, and we're going to consider whether they could be acidic or not, and if one of them could, which one of these would be more acidic than the other. All right, so let's remove one of those protons. Okay, so we're going to get to here. If we remove a proton, we're going to have a minus charge here, plus H+. If we do the same thing for this situation, we get this anion plus H+. All right, so which one of these would be more acidic? Which is more acidic? So let's compare the stability of these conjugate bases. All right, so what do we know about this type of structure? All right, it's cyclic. Right? It could have a p orbital in every position. If we put a p orbital here, it could be planar. So what do we have to add in here? We have to consider in its stability how many pi electrons. right? So how many pi electron pairs does it have? Well, it has 1, 2, 3, 4. It has 4 pairs of pi electrons. All right? So does that make this molecule very stable? No, this would actually, if it was planar, would be anti-aromatic. All right, so this was not a very stable conjugate base. All right, what about the bottom one? Okay, again, we have we have a ring. We could have p orbitals on all if we make this position here be sp2 hybridized. Could be planar. So how many electrons do we have here? We have 1, 2, we have 3 pairs of pi electrons. So what does that mean for this structure? This structure is aromatic, right? So that means that that conjugate base is very stable, right? So very stable conjugate base. All right, so what does that mean about acidity? All right, so it means that this one should be more acidic, less acidic. All right, and in fact, this bottom one is so acidic, the pKa of this is actually 16. All right, so what other molecules have pKa's at 16? Right, this one is basically the same pKa as water, right? pKa of water is 15.7, or alcohols, which have pKa's around 16. So here's a compound that has a carbon-hydrogen bond that's acidic as the oxygen-hydrogen bonds of water and alcohol. So that is super strange and really cool. All right, I'm sure you agree. All right, so we're going to turn this back around, reverse this a little bit. In this case, we're going to pick one molecule. This is imidazole. All right, we talked about this is aromatic. And notice that imidazole has two different nitrogens, and each of those nitrogens has a non-bonding pair of electrons. So in theory, either one could act as a base and react with a proton. So what we would like to figure out here is which of the two nitrogens is more basic, which of the two is more apt to pick up a proton. Okay, so what we're going to do in this case is we're going to draw out the conjugate acids, and we're going to figure out which conjugate acid is more stable, and that one is going to tend to form more readily. All right, so this is going to react with a proton. We're going to protonate nitrogen A first. Okay, so we already have an H on there, so we add another H. It's going to put a plus charge, double bond, non-bonding electrons. Okay, so this is one conjugate acid. Remember, if we're making a conjugate acid, we always add a proton. Okay, if we add the proton to the other position, all right, so now we're going to put an H here with a plus like that. What about this structure? All right, so which one of these is more stable? Okay, so it turns out the bottom one is much more stable, right? Because this one, for one thing, is still aromatic, right? Because all we did is we did this reaction with these electrons, which are in the sp2 hybridized orbital. When we did the reaction for nitrogen A, this pair of electrons had been in the pi system, but now we used it to form a nitrogen-hydrogen bond. So up here, this position is now sp3 hybridized, and we can't have an aromatic compound with an atom in the ring that's sp3 hybridized. right? We can see this even farther by the fact that we can have resonance like this, that shifts the double bond up here in the plus, and the pair of electrons down here. So we could draw additional resonance, but look at, we have these two resonance forms that are identical to one another as well. Okay, so this is much more stable, means it forms more readily, and so nitrogen B, this one here, is more basic. Okay, that's the one that tends to react more often with a proton. Okay, so in this quick video, what we've done is show our first example about how aromaticity and how resonance can influence the reactivity or the reaction outcomes. We've looked at how resonance can stabilize either conjugate bases or conjugate acids and shift the equilibrium one way or another.